Natural warm water springs form the ideal habitat for the amoeba Naegleria fowleri. This protist causes a very rare form of meningitis. The amoeba is inhaled and burrows through into the brain from the nose. Once in the brain, a rapidly fatal meningitis ensues. Bathing in the Roman baths in the city of Bath is no longer permitted because the water source of the baths is contaminated with Naegleria fowleri. This is an example of a waterborne infection whose symptoms are exclusively extraintestinal. Sanitation has been of immense benefit to us. The Romans had highly developed water engineering systems and pioneered public lavatories and sewer systems. With the fall of the Roman Empire, however, these engineering feats that did so much to preserve public health were largely forgotten. For populations that were largely rural, this was not a very large problem, although in Elizabethan England there were measures in London to warn inhabitants to keep the channels against their houses free from filth and not to make dunghills out of the stables in their streets. These measures were admittedly aimed at helping the populace to protect them from plague, but it shows an embryonic awareness of the threat to public health posed by excrement. Although the etymology of the Khoi term loo is somewhat obscure, there is a popular school of thought that runs that it is a contraction of the term gardez l'eau, shouted to warn pedestrians below that the callers were about to empty the contents of their chamber pots from their bedchambers to the streets below. Only with industrialization, when unprecedentedly large numbers of people started to congregate in cities, did disposing of sewage become a problem. Things became so bad that during the summer of 1858, the foul, noxious smell emanating from the Thames caused curtains soaked in chloride of lime, a powerful bleaching agent, to be hung at the windows of the Palace of Westminster. Once MPs were discomfited, it was not long before the action was taken. One of the triumphs of the 19th century was the recognition of water as the vector of life-threatening infections, and the efforts of engineers to provide clean drinking water. Joseph Bazalgette was the engineer who was responsible for building networks of sewers that cleaned the water supplies in central London, ensuring that it would never again suffer from the great stink. His monument on the embankment bears the legend, Flumina vincula posuit. He placed the river in chains. Microbiological examination of potable water is really important. Because of the risk to human health caused by waterborne infections, in developed countries, microbiological monitoring of water supplies is regularly undertaken. There are many waterborne infections, and it is impractical to test water supplies for the presence of all of these possible causative agents, particularly since these organisms may be present in very small numbers. And they also tend to die out rapidly. It is therefore the practice to test for the presence of fecal indicator organisms. These represent the inhabitants of the mammalian gut and are found only in the bowel or in areas contaminated with feces. The qualities required of a good fecal indicator include the ability to survive in all water sources that act as potential drinking water supplies, the presence wherever and whenever the enteric pathogens are found, the ability to survive in water longer than the hardiest of the enteric pathogens, the inability to reproduce in contaminated water, otherwise an overestimate of the degree of fecal contamination of the water source will result. Typically, 3 bacteria are used as indicators of fecal pollution: Escherichia coli, Enterococci, and Clostridium perfringens. Water supplies may be tested for the presence of all 3 bacteria, but it is usual practice to look only for Escherichia coli. The coliform group of bacteria can be found in the guts of a diverse range of animals and birds. It is thus possible to isolate these bacteria from waters distant from human fecal contamination. It is also necessary to distinguish fecal coliforms, such as E. coli, derived almost exclusively from intestines, from other members of the family Enterobacteriaceae, such as Klebsiella pneumoniae, a bacterium that may also grow in soil and upon vegetation, and whose presence in water need not result from fecal contamination. In the case of E. coli, water supplies are first tested for the presence of coliform bacteria, including all the lactose-fermenting coliforms. These may or may not be of fecal origin. This test is referred to as the presumptive coliform count. To ascertain the numbers of E. coli present in the original water sample, bacteria from the presumptive coliform count are subcultured into media in which only fecal coliforms normally grow. This permits the differential coliform count to be determined and provides an estimate of the numbers in the original water sample. Finally, to distinguish E. coli from other fecal coliforms, the IMVIC tests are used on colonies subcultured onto solid medium from the differential coliform test cultures. E. coli is typically positive for the production of indole and in the methyl red test, but it is negative for the Vosges-Proskauer reaction and in the utilisation of citrate. The initials of these tests provide the acronym IMVIC. Enterococci are more able to survive in brackish waters than are fecal coliforms, and they provide a more reliable indicator of recent fecal contamination in such sites. The presence of enterococci is sought where there is difficulty interpreting the results obtained from coliform counts. The absence of enterococci does not, however, exclude the possibility that the water sample tested was contaminated with feces. Sporing anaerobes are highly resistant, and their presence in the absence of other fecal indicators points either to distant fecal pollution or to the sporadic contamination of water occurring at some time previously. As with fecal coliforms, a presumptive clostridial count is performed initially, and subsequently the presence of Clostridium perfringens is confirmed by the production of a stormy clot in litmus milk cultures. There are two commonly employed methods of testing waters. When small numbers of organisms are expected, the membrane filtration technique is employed. This method gives good reproducibility and allows very large volumes of water to be examined easily. This greatly increases the sensitivity of the count. However, it cannot be used to count bacteria in waters of high turbidity, nor in waters that have large populations of aquatic bacteria, since these may overgrow the fecal indicators. Furthermore, heavy metal ions and phenolic compounds present in the water samples may concentrate upon the filter material, inhibiting the bacterial growth, and so lowering the observed counts. Consequently, in some situations, the more expensive and technically much more demanding most probable number method is used. This exploits a variety of selective media. Although the bacteriological examination of water is regularly undertaken, the virological testing of drinking water is less common. Many viruses that cause waterborne diseases cannot be cultivated readily in the laboratory. They may also persist in water for longer than bacterial fecal indicator organisms. The inoculation of test water samples into tissue cultures and the subsequent examination for plaque development has been employed, but these tests are confined to specialized laboratories. To circumvent these problems, it has been proposed that bacteriophage may act as virus indicators, highlighting water that may potentially be infected with viruses. However, the practice of examining drinking water for viruses is not widespread. Perhaps this is an area where the application of molecular biological techniques, such as the polymerase chain reaction or PCR, would prove of value, but only if the results are treated with caution. PCR will detect total virus genomes without differentiating infectious from non-infectious particles. Our ability to test for waterborne infections using fecal indicators has meant that we now have, and we take for granted, clean water. In the third world, people don't have that luxury, and as a result, they are still suffering and dying from waterborne infections that could so easily be avoided.